Hello, everyone, and welcome to the first seminar of our winter series in 2022. I hope you're all doing well, and especially given still these challenging times of the pandemic. So as you're well aware, our civil seminar series this term will be virtual. And well, that allows us to invite high-profile researchers and experts professionals like our today's speaker, and which is a benefit of this. We're not bound by physical distance. So today we are very pleased to have Dr. Keith Porter with us. As a quick background, Dr. Porter serves as Chief Engineer of the Institute for Catastrophic Loss Reduction. He specializes in multi-hazard risk to buildings and lifelines. Dr. Porter has led natural hazard mitigation saves, which is the most cited benefit cost analysis of natural hazard mitigation ever. He has led engineering for the U.S. Geological Survey's shakeout, arc storm, tsunami, and haywire disaster scenarios. He also pioneered second-generation performance-based earthquake engineering methods underlying FEMA P-58, which is the global state-of-the-art in seismic design. He has written 230 works on risk management and is a fellow of the American Society of Civil Engineers and the Structural Engineering Institute. Dr. Porter holds professional engineer license in California and Colorado, and he has received civil and structural engineering degrees from UC Davis, UC Berkeley, and Stanford University. And today he has kindly agreed to share some of his professional and personal experience through this long path with the topic of a Brownian particle in a career maze, my idiosyncratic path to a profession in disaster resilience with a general lesson for enjoying your job. And with that said, I welcome Dr. Porter to please go ahead and share your screen and present. Thank you.
Great. Thanks, Dr. Najafi. Hi, everybody. Welcome to the beginning of the semester. Dr. Najafi tells me that you're interested in hearing about, hang on a second, let me get a screen out of the way so that I can see my speaker notes. You're interested in hearing about career journey of your speakers and their academic and industry experiences. He asked me for any advice I would give you about your future success. I know of at least two general principles for planning a career. One where you pick a star and you steer toward it, and one where you take the next step in front of you and follow it with another and another. Oh my gosh, hang on a second. I still have to move this thing around. Just a moment. Now, an approach where you pick a star and you steer toward it would have never worked for me. An interviewer or two over my career have asked me where I plan to be in 5 years, and I don't recall my answers. But aside from satisfying the interviewer, getting me past that next step, the answers to those questions were totally immaterial in my life. My career never worked that way. I'll start at high school, the beginning of when one begins to start thinking about planning a career. I had diverse interests that included creative writing, and architecture and science. I won a prize for with the San Francisco chapter of the American Institute of Architects for that drawing in the middle. But you can't study to be a writer and an architect and a physicist. You have to choose a major at a university. but you can keep your interests alive. Sorry, the poll was popping up. And that's what I did when I went off to study civil engineering at UC Davis. My second career, which I planned toward the end of university, was to build big things as a construction contractor. I helped to build a prison, shown in that satellite image on the left, in Central California, in a place called Avenal. The picture on the right is a view from the highway outside of that prison. I worked part-time senior year and the first summer after graduating in that career, but that career ended quickly when I found that construction contracting in California in the 1980s involved about half my time spent fighting with the construction manager and living in places like Avenal. But I came away from that job with a certain skill set, the basics of construction contracting and construction cost estimation. When that prison contract was done, I declined to sign up for the next project and took a job instead as a bridge designer with Lytton International. I designed this bridge on the Taipei MRT system. I also designed these, you can see these sort of sound barriers here. The red thing, the thing with red stripe down it. And I designed these little wings on the tops of the columns, and I designed that column capital, and I wrote the general specifications for this project. That job lasted only a year because I couldn't sleep for fear of my bridge collapsing and killing people. Turned out that a bachelor's degree was insufficient for responsible charge of the design of a bridge. My employer didn't think so, but I did. I learned along the way how detailed design of structures works, about quality assurance, about base isolation. I learned some basic Chinese language, and I learned that I loved international travel. So I went back to graduate school to learn to be a better designer with the expectation that I would go back to work with Lytton and be able to sleep at night after having designed a bridge. So I went to graduate school and then quickly jettisoned that career plan when I met these two professors. Ritelmo Bertero, here on the left, introduced me to the then cutting edge of structural engineering, which is seismic design. And then the 1989 Loma Prieta earthquake came along while I was preparing a lab plan for my master's thesis advisor, Hassan Astani, shown there in the middle, who was contracted by the California Department of Transportation after that earthquake happened to go out onto the San Francisco-Oakland Bay Bridge, where this little collapse happened, to figure out what had gone wrong while the bridge was being repaired. And that was all just too exciting to go back to work for Lytton designing bridges. I was hooked on earthquake engineering. I stayed 2 years at UC Berkeley instead of the one required to get a Master of Science degree. I got a Master of Engineering degree. And I stayed because there were so many exciting courses. I took seismic design, I took geotechnical earthquake engineering, I took seismology, architectural history, and pretty much anything else they would let me take within the limited number of units you can take in 2 years. And I took these classes from some of the then world leaders in earthquakes and structural engineering. When I graduated from Cal, when I got my master's degree at Cal, I took a job with a leading earthquake engineering firm called EQE International, which then was the largest privately held company specializing in earthquake risk. My first job with EQE was seismic rehabilitation. That was designing retrofits for existing infrastructure. I designed the seismic retrofit for this unreinforced masonry textile factory, which is now a self-storage warehouse in San Francisco. One of the retrofit options was internal steel braced frames like you're seeing here on the right. I did seismic retrofit for the East Bay Municipal Utility District's wastewater treatment plant at the east end of the San Francisco-Oakland Bay Bridge, and that involved things like bolting down pieces of equipment onto their concrete plinth, like this piece of electrical equipment shown on the right. Now that career lasted about 2 years, though I came back to it later. It was a lot of fun, but I had a very unpleasant supervisor and really because something better came along. Along the way, I learned, in those 2 years, I learned the nuts and bolts of rehabilitating existing buildings and other infrastructure, including those non-structural components like I just showed you. But the something better was catastrophe risk management, working for a division of EQE called EquiCat. We made models, computer models of the behavior of collections of assets like buildings, subject to probabilistic hazard like hurricanes, where the model estimated the wind speed or the earthquake shaking or the depth of flooding or whatnot, and the damage it would do to all the assets, the buildings and so on, and the repair costs and the insurance losses and other aspects of disaster performance of those assets. And I did that for the next 4 years or so. From about 1993 to about 1997, I was the vice president and janitor of EquiCat in Tower 2 of the World Trade Center in New York City. I came back to that career a little later on. I got to do applied research, developing those models. I learned about insurance and reinsurance. I learned about fragility and risk, but after about 4 years, the repetition kind of got to me. And the fact that I did the applied research that somebody else with a PhD assigned to me. I wanted to decide what to develop, what models to develop and how. And that took me to Stanford University to get a PhD. I had an idea about how to estimate the future performance of buildings and other infrastructure without relying on historical loss data. That is, using analytical methods to estimate the future seismic performance of buildings and other infrastructure. I developed this. It's what in my thesis I called assembly-based vulnerability, and has since been subsumed under the names performance-based design or second-generation performance-based earthquake engineering. And here's how it works. In the 1990s, when you did structural design, you designed to meet pass, no pass criteria that are in a building code. And I realized that you could design to meet performance objectives. That is to say, you could design a building and check how well it performed in terms of its future probabilistic performance in terms of repair costs, life safety impacts, and duration of loss of function, or as I term it, dollars, deaths, and downtime. I loved that research so much that I wanted to become a tenure track professor. After 3 years of PhDing, my career as a tenure track professor actually never began. In 2000, when I got my PhD, the National Science Foundation wasn't particularly interested in analytical research. It was putting all of its money into experimentation in earthquake engineering. But I did learn along the way how to become an expert, how to do a literature review, how to develop how to advance from the current state of the art or the current state of the practice with something new. I developed methods to pull together probabilistic hazards, statics, dynamics, construction contracting, and those performance measures, those dollars, deaths, and downtime. And although I couldn't go on to become a tenure track professor, I spent some time as a postdoctoral scholar and as a research professor. That is to say, somebody who doesn't teach, but just does research. And I also opened a small engineering risk consulting company called SPA Risk. So over the next several years, I started doing directing my own research. These are 3 examples of that. The picture on the left is the first performance-based earthquake engineering analysis of wood frame buildings. The one in the middle is the first version of a US national benefit cost analysis of natural hazard mitigation. That became in its day, the most cited, most exhaustive benefit cost analysis of disaster mitigation ever. And the document on the right is FEMA's P58 guidelines for how to do this second generation performance-based earthquake engineering, the stuff that I originally called assembly-based vulnerability, but kind of got subsumed into this under this term performance-based design. That career has lasted the last 20 plus years. And it's taken many turns. I have followed new directions, creating new methods for performance-based engineering, finding and solving new problems. And with every new problem, I developed a new tool or a new set of tools. So imagine over time a linearly expanding tool chest of techniques with geometrically expanding combinations of being able to put this together with that to solve a new problem. And it also taught me respect and interest in a diverse set of other disciplines. I became interdisciplinary. After that, after about 20 years of research professoring and engineering risk consulting, I wanted to come to Canada, and I found the opportunity to do that through the Institute for Catastrophic Loss Reduction, where I'm now the chief engineer, which allows me to branch out even more broadly into other perils that I never considered before during my academic career. So let me sort of wrap up this part of my talk with a metaphor for my career path. My career path did not look like the image on the left, where you just decide, am I going to go into construction contracting? Am I going to go into bridge design, or am I going to go into catastrophe risk management? I showed you a path of 8 careers. They much more resemble that pathway, much more closely resembled the image on the right, where I chose an interest. I went through a door. I discovered that I gathered some skill set in that room, and that experience opened doors to new opportunities. The opportunities change depending on which doorway you go through, and you're not going to know what opportunities come afterwards. At least I could never predict what opportunities were going to come afterwards. So even though this picture shows a sequence of open doors, you can imagine it more like opening a door, going into that room, learning something, and then discovering that there are additional doorways that you can go through. You open one of those doors, go through it, etc. So here's some takeaways from 8 careers, or maybe I could call them 8 careens, because I felt that I went careening from one career to another. What worked for me was to gather knowledge about anything that interested me. I watched for opportunities to use it. And when those opportunities came along, I chose the ones, I made choices, and those choices were entirely under my control, right? I never had to rely on somebody else saying, okay, you may go on to this career path where you'll get where you plan to be 5 years from now. My choices were always about, what can I do now? What can I do for the next 6 months or the next year or something like that? It was never, what can I do for the next 5 years, at least not until much later in my career. What didn't work for me was an answer to the question, where do you see yourself in 5 years? That sort of thing can work in many careers, but it did not work in mine. Now, I don't think my experience is all that uncommon. Now, there are people who do go through college and they get their PhD and they go on to be a research professor or a tenure track professor, and that's what they do for the rest of their career. But there are a lot of people who do something different, who follow a career path like mine. Let me give you an example, 2 examples from 2 colleagues who started out in very different places and ended up in the same one. The lady on the left is Kate Long. She started in film. She worked for Universal Studios and doing project management, that sort of thing. Then in the 1994 Northridge earthquake, it shook her out of bed at 4 o'clock in the morning. After she cleaned up the glass on her kitchen floor, she went into work, and she and another colleague just spontaneously took command of Universal Studios' response to the earthquake. They created a spreadsheet that kept track of messages about building damage and making sure that somebody went out to inspect those buildings. That led her into an accidental career in emergency management. She went on to work for the California the California Governor's Office of Emergency Services. She did that for 10 years or so. When she retired from Cal OES, she went to work for a science think tank called the Lucille Jones Center for Science and Society. The woman on the right is Lucy Jones herself. She started her career with an interest in the Chinese language, music, and seismology. And by accident, she had an opportunity to be the first Westerner to go to China and study a big earthquake that happened there, because she spoke the language and because her parents had been missionaries in China. Totally contingent opportunity that arose and launched her down a career path. She became a leading seismologist. She came back to Southern California, got a job with the U.S. Geological Survey as a seismologist. And then the 1984 Morgan Hill earthquake came along. She happened to be the scientist in charge of the office in Pasadena, California, when the press rolled up to learn about what had happened in this earthquake. That day, she had no babysitter and she had a baby. So she spoke to the press, to Los Angeles and Southern California about what had just happened in this earthquake, with her baby Lars in her arms. That launched a career as the earthquake lady. She has become known as the earthquake lady in Southern California. Southern California's expert, its font of knowledge on earthquakes, and more generally in natural disasters. When she retired from the U.S. Geological Survey, thanks to some very high-profile projects, she started a think tank, the Lucille Jones Center for Science and Society, where she now works with my other friend, Kate Long. All right, so my point here is that for a lot of people, a career path means taking advantage of opportunities as they arrive, following your interests as they are today, and realizing that your interests may change, your skill set may grow. You just follow if you follow your passions, as Wayne says in Letterkenny, do what you love and you will never work a day in your life. Okay, so that's my career path, but I would like to tell you a story of a recent artifact of this sort of random walk, a little bit more nuts and bolts engineering-y. Let me tell you about a recent project I performed for the Institute for Catastrophic Loss Reduction, where I estimated the benefits and costs of the National WUI Guide. This is a design guideline being developed for Canada on how to design better for buildings that are situated in the wildland urban interface, the WUI. Let me give you the business case for fire-resistant design in the WUI. Now, Canada is suffering from the climate crisis with the rest of the world, and is suffering a steadily increasing frequency and severity of catastrophes in the wildland urban interface. What Canada has learned through the Fort McMurray fire and Lytton and others is that everybody pays for natural disasters, even those people who are outside of the WUI. We really are all in these natural disasters together. If you wonder how everyone else pays for Fort McMurray, everyone else pays for Lytton, it's because the nation has to respond to those disasters. It has to help people recover, and so on. And so we all pay through taxes and through impacts to the economy and so on. The National Research Council produced this guide on how to build better. My job was to estimate its costs and benefits and to find the business case to follow that guide. So I'm going to take you very quickly, I have time, through the objectives, the methods, and the conclusions of that study. The objectives of this impact analysis were to perform a benefit cost analysis of complying with the WUI guide. We created a statistically representative sample of existing buildings, all subject to differing levels of fire hazard. We created a statistical sample of new buildings at those hazard levels. We then estimated the benefits and costs for those sample buildings, and then scaled up to the community and the national levels, including community costs, and we estimated benefits by a number of benefit categories. We produced this report, a 5-page overview on the left, and a 136-page scholarly report on the right. This is how you do a benefit cost analysis. You start by characterizing the assets at risk. You characterize the hazard to which those assets are exposed. You characterize the vulnerability of those assets, that is to say, the degree of loss given some level of excitation like ground motion. You then characterize the damage given the vulnerability, and the loss to recover from that damage. That is to say, the repair cost, life safety impacts, the loss of function to recover that damage. You iterate to account for all the probabilities. You calculate the present value of future losses. You calculate the benefits with and without mitigation. That is to say, the present value of loss with and without mitigation. The difference between those two values is the benefit of that mitigation. The benefit cost ratio is then the sum of the benefits divided by the cost. And if the benefit cost ratio is greater than 1, that indicates a desirable investment. The higher the benefit cost ratio, the more desirable in the investment, because the more benefits there are per dollar of cost. One can characterize a variety of different loss categories and include them in the benefit ratio. Those can include the repair cost for infrastructure, other property loss like contents, direct and indirect business interruption, the cost of displacement, the value of safety, the cost of medevac, post-traumatic stress disorder, a variety of other benefit cost categories beyond basic dollars, deaths, and downtime. As applied here in the National WUI Guide, we sampled 102 houses in 9 towns. The towns span from east to west and low to high hazard. We chose 2 older buildings from that sample and 2 newer ones to represent typical cases. We used new information from the from CAL FIRE, the fire agency for the state of California, to estimate the probability of ignition and probability of loss. We estimated benefits and costs. We estimated the costs and benefits for 15 options per house, 3 different levels of exposure. I won't get into what that means. 5 different options for vegetation management. I won't get into those details either. And we accounted for climate change and demand surge, which is an increase in losses in very large catastrophes. The increase in loss has to do with increase in prices, labor prices for the most part. These are the 9 communities. Oh, sorry, hang on a second. Sorry. All right. Unfortunately, I have a audio recording. I hope that is not playing audibly to you. Can you, somebody chat? I had to turn down the speaker to turn off the audio recording. Is anybody hearing the speaker going on behind me?
It's all good, Keith. Oh, now it's good.
Okay. Anyway, I'm assuming the answer is no. These are the archetype houses. One of the archetype houses, some of its attributes in terms of square footage and repair cost and whatnot. These are the compliance costs per square foot to make it comply with the National WUI Guide. These are the 15 options I talked about, depending on the level of exposure, which has to do with the proximity to vegetation, and the yes, I will give you a copy of this presentation. And the 5 options that are in columns are whether you want to solely make the building fire resistive through structural measures or through control of vegetation or something in between. What we found was that the cost to comply with this guide amounted to about anywhere from $2 to $20 per square foot, and it varied depending on which option you wanted. Now, vegetation management requires cooperation of many neighbors. In this picture, you're seeing a contour of 10 meters where you can control your vegetation, but that covers 3 properties. You can control your vegetation out to 30 meters. That's the yellow perimeter that covers 7 parcels, or you can control the vegetation out to 100 meters, and that covers 25 parcels, which means all those people have to cooperate. We use some research by Gower and others to estimate the rate at which WUI fires occur in any given location. This map shows 15 zones of tree species, weather, lightning strikes per year, and so on. The California Department of Forestry and Fire Protection, that's CAL FIRE, provided data about 1,000 houses that experienced the 2018 Camp Fire. This chart shows the likelihood of a building being ignited given various attributes. The left-hand box shows that if it's got a wood elevated deck or porch, it had a 2.5 times greater likelihood of igniting compared with whether it had a composite deck or masonry or concrete deck or no porch or roof. And you can see that there are these charts for deck and porch on grade, whether the eaves were enclosed, etc. We use these data to estimate the probability of ignition for various different conditions of compliance and non-compliance. So some findings and conclusions about the WUI impact analysis. We found that at the national level, accounting for hazard and population, if the entire country followed the WUI guide, it would save $4 per dollar of cost on average, and up to 14 to 1 in communities in the high hazard areas. That's the benefit cost ratio, including the cost to the community, like better roads and firefighting water supplies. These 2 charts show where those benefits come from. The left-hand chart reflects retrofitted existing buildings, and the right-hand chart reflects new construction. Each chart shows 9 slices, 9 categories of benefit, like about 30% of the benefits come from lower building repair costs. The charts are pretty similar. Now, here's some top 10 conclusions. First, the WUI guide makes great business sense. At the house level, building new to follow the guide can save $34 in avoided future losses per dollar of capital and maintenance costs. I said 14 to 1 earlier, but that included community costs. The homeowner's direct costs are only part of that, so their benefit cost ratio is higher. 34 to 1 BCR is very good, suggesting a very desirable investment. Retrofitting costs more, but the BCR can still reach 14 to 1. Again, that's just considering the homeowner's costs. I already mentioned the community level benefit cost ratio of 14 to 1 in high hazard areas. At the national level, accounting for all hazard levels, Canada would save $4 per dollar spent. It would avoid $500 billion in future losses at a cost of $125 billion. It would create 20,000 long-term jobs, save 2,300 lives, avoid 17,000 non-fatal injuries and instances of post-traumatic stress disorder, and avoid $1 billion in lost tax revenues. Compliance via vegetation management, sometimes called nature-based solutions, costs 1/3 as much as doing everything with structural changes. So the benefit cost ratios can be 3 times as high, and in fact as high as 100 to 1 for the homeowner. Indigenous communities have long engaged in that kind of approach to managing fire risk. Vegetation management requires community cooperation, but the payoff is huge, as I mentioned before. Everybody saves, even people not in the wildland-urban interface. Climate change will make fires more likely and fire-resistive construction more urgent and more beneficial, adding about 40% to benefits relative to our current climate. Municipalities and electric utilities have a role to play with better water supply for firefighting in some places and better maintenance of vegetation around electric distribution lines in many places. Now, there's more to tell about the study. We estimated benefits conservatively low. We omitted pets and mementos and other categories that are hard to quantify. And the study leaves a number of important questions unanswered. about questions about climate change, about social issues, and about and other topics. You will find this deck at that URL. I made some last minute changes, so after our class is over, wait 15 minutes or so before downloading the deck. But I will text you this URL so that you don't have to quickly write it down. And with that, I will take questions.
Thank you very much. So reports are very interesting and quite useful, I'm sure. And looks like with the in this
I have a question, Reza, for Keith.
Yeah,
Okay.
That's what I was going to say. Yeah, please go ahead
Yeah.
and ask questions if you want.
Yeah.
Hi, Ashraf, how are you?
Hello, Keith. How are you?
I'm fine, thanks.
Good, good. Thank you for the very interesting presentation. I have my question is, how do you see performance-based designs that was developed quite well in earthquake engineering can be applicable to other disasters? And particularly, I want to ask you about wind and also more importantly, floods, because we see a lot of structural damage coming mainly from floods. And to my knowledge in structural engineering, the research done from a structural point of view on floods, it's very little compared to earthquake for sure, and even compared to wind.
I think that performance-based engineering can be applied to a lot of different perils, certainly to flood and wind. Others have developed performance-based wind engineering for quite some time. That work began shortly after peers started publishing performance-based earthquake engineering. And the power of performance-based engineering is that you don't have to wait for a disaster to occur. As long as you can estimate the engineering impacts of the water level or of the wind speed in terms of member forces, member deformations, or other kinds of stresses on structural and non-structural elements, you can create a forward model of the environmental excitation, for instance, the depth of water, the structural response in the case of wind, forces on, connectors and whatnot, the physical damage, for instance, in the case of flooding, the growth of mold or the damage to gypsum wallboard, etc. And then calculate the cost to repair all those physical damages, the cost to rip out the gypsum wallboard that got wet, for instance. And the great value of being able to do that is that you can estimate the costs and benefits of alternative design without waiting for an actual disaster to occur, right? So come up with a new way to design to make a building wind resistant, and you can estimate the cost of doing it so, and you can estimate the benefits of doing so in apples to apples terms of dollars and deaths and downtime for cost to repair. And you can talk about the probability that you're going to get some benefit from that added cost. I think that there's really the only limit to the use of performance-based engineering is the credibility of the answer that comes out of it, right? It's all forward modeling. So you get an answer, you just don't know if it's right, and that's where having some empirical evidence really helps. With flooding and with wind, we may not be able to test the credibility of a model that involves this, that, or the other particular structural detail, but we can tell whether our models are within the ballpark of experience. So anyway, I see great potential, great power, although with some limitations to the power of performance-based engineering. Reza, do you want to moderate, or shall I pick someone, or what?
Yeah, please. We can start with Nikon. Please go ahead, Nikon.
Hi, everybody. Sir, thank you for a great presentation. I was wondering to know if the research area you're working in is related to our video reality-based design optimization. Just because I'm a little bit familiar with structural optimization and finite element modeling, so I want to know that how much professors are interested in these topics.
How interested professors are with optimization?
The mix between optimization and design.
Well, professors usually want to create new methods to calculate stuff. So we like, and now speaking as a professor rather than as a practitioner, we like novelty, we like tools to calculate things that we could never calculate before. And we like to learn the lessons that you can gain, the insight that you can gain with this new tool that you couldn't gain by some other method. So if the particular approaches to optimization provide new insight, then you're going to be able to find a professor who wants to pursue it. Now, engineering practitioners have different goals. They want a competitive advantage. They want to be able to tell a client, I can design this building to be cheaper and still accomplish the same thing. Or I can design this building to minimize cost and maximize some other performance measures, such as, I don't know, the chance that there will be some costly damage, minimize the chance that there will be some costly damage. So the tools like optimization, where they can provide a business advantage, you will find engineering practitioners who will, ask you to tell them more.
Okay, the fact is that I'm looking for some PhD opportunities, but I don't know which type of PhD studies are really, which professors are really interested in interdisciplinary connection between optimization and civil infrastructures.
I think the only way to find the answer to that question is to search everybody's webpage, look for keywords, if like interdisciplinarity or optimization, and then you go talk to them one after another. And maybe in the meantime, you do some literature search. Find the papers that are closest to your area of interest, and who wrote them, and go talk to those professors. It's just
what about yourself, sir? Are you going to recruit some people with this background?
Myself, I'm at the moment, I'm not. I am an adjunct professor at University of Colorado Boulder, and I'm advising a couple of master's students there, but I'm not taking on new master's students here. I may become an adjunct professor here, and we will see what opportunities arise if and when that happens.
Okay,
thank you.
I suggest you can contact the professor.
Thank you so much.
Let's move on. Majid, please go ahead and ask.
Oh, you're muted, Majid.
You're on mute, Majid. Please unmute yourself. We can't hear you. You're on mute, Majid.
Okay. Yes, sir. Thank you. Yeah, hi, Professor. Thank you for coming this seminar. My question is I want to make use of your experience in terms of being a distinguished professor, an expert like you. How we can reach the summit of the success, like you specifically in structural engineering. My question is, do you think the approaching, for example, enrollments and studying in institutes, professional engineering institutes beyond and after graduation, do you think it's a good policy, good strategy for becoming a distinguished designer, structural designer? or it's wasting time?
I think it's all contingent. This is that it's that very approach to planning one's career that I am worst at. I never was able to say, okay, if I want to get there, 5 years from now, 10 years from now, 20 years from now, here's what I have to do to get there. That's not the way my career went. And I don't know, how many people that works for. I'm the wrong guy to ask about, how to get where I got. I got here entirely by contingent opportunities, following things that were of interest to me, not through a deliberate plan to become, preeminent at anything. Sorry.
Thank you for the response.
Sure.
So Dr. Porter, I have a question. So in your risk analysis, because we know that hazards have this stochastic nature, what is your approach to basically bringing uncertainty in your assessments?
Well, it starts with recognizing what parameters within one's framework, within one's model, are uncertain, and then attempting to estimate their probability distribution, and then using any of several methods to propagate uncertainties through the model. Most commonly, we use some version of Monte Carlo simulation. And there are expedients you can follow to decide which parameters matter to the the output that you care about, the ultimate dependent variable, whether it's dollars, deaths, or downtime. There are deterministic sensitivity studies that you can do to say, okay, well, the uncertainty in this parameter matters and the uncertainty in that parameter doesn't. And then you take the ones that seem to matter, that seem to affect the uncertainty in the dependent variable, and you use Monte Carlo simulation or any of a few other techniques to propagate uncertainty through the entire analysis. It's just basically the theorem of total probability, is basically how you do that.
Right. Thank you.
Sure.
Excellent. Again, thank you very much, Dr. Porter, for this very interesting talk that covered both of the aspects we were interested in. Both it had the personal experience and things you have learned through this journey and sharing that with us and going through a project. And I appreciate that. Thank you very much. I'm glad you have joined us and you're physically at Western, and I hope to have you with us to present in our future seminar series as well with the other topics. I'm sure you have much to share with us. And thank you everybody for attending this seminar. We'll look forward to seeing you all next week on Tuesday.
Yeah,
Thank you again.
While we are here, can we meet briefly together for a few minutes?
Sure. You want to come over?